All right. So just going to be finishing up 6.4 calorimetry and then 6.5, which is about phase changes, and then I'll have a second video for the rest of this at some point this weekend. So let's take a look at this example. Hopefully, after talking in class and actually seeing a real example of calorimetry, this has a bit more context and a bit more, hopefully, a more thorough understanding of it. But let's look at some examples. So one thing they like to give you is a graph showing the temperature over time, or they could give you a table of the different temperature values over time. And we have a piece of metal that is hot, and then we put it in water, and then, or sorry, we're just heating up the metal, and we're just talking about how much it heats up. Just kidding. And it's asking for the temperature change. So from the graph, and it's time on the axis. So here's my starting temp, and here is my ending temp where it plateaus. So my temperature change, always T final minus initial. Final temp is 60 degrees Celsius. Starting was 20 degrees Celsius, meaning that your net change was 40 degrees Celsius. Sick. And then it is asking to determine the specific heat capacity of the metal, including units. So we know that this much heat was added to our system. So that is our Q value. The heat is how much was added. That's our mass. This is my delta T. So we know that Q is equal to MC delta T. And here's my unknown. So I'm just going to rearrange for that just to make the algebra slightly less difficult. So I should put positive 440 joules. My mass, 27.00 grams times my temperature change. So that should be that my heat capacity is 0.41 joules per gram degrees Celsius. So again, the units will get more tricky on some problems where they're mixing it up on you. So always good to keep track of those units. Be careful about it. In this case, it's just a standard specific heat capacity. Like these are going to be your units most of the time. But good to keep track of. Sometimes what if they gave you this in kilojoules, or what if they gave you this in Kelvin, or whatever. Got to make sure that you're plugging in what you want. All right. Our next thing is talking about dissolving a salt in a calorimeter. So first of all, let's look at based on the data, is our process endothermic or exothermic? So let's look over here. And you might notice that my temperature has changed from this to this, indicating that it has gotten warmer. So from this solution being dissolved, I've had an increase in temperature, showing that heat was released from this process, causing my solution to heat up. So I know that this process is exothermic. And just from that data, so because the temperature of solution therefore Cool. All right, and then it's asking us to find the mass and find of the solution and of the salt. So of the solution, that's the whole thing. So solution implies that we have it divided together, right? Or sorry, added together. So we're going to take this one minus the mass of the calorimeter. So the mass of the solution is equal to whatever that was, 61, yeah, 61.54 grams minus 11.31 grams, which means that the mass of the solution is this. And then the mass of my salt. To get that, I can subtract my total versus before I added it. So that would be 61.54 grams minus 56.57 grams, which means that my salt was this many. So we assume they're additive unless told otherwise. Okay, to determine the net change. So we got delta T is always the final minus initial. So the change in temp was 36.5 degrees Celsius minus 20.0 degrees Celsius. Means the change in temp was 16.5 degrees Celsius. Cool. Okay, calculate the number of moles of calcium chloride that were dissolved. So we know our mass of our salt, and we know our molar mass, grams to moles. Okay, so from dissolving this much of our salt, we saw a temperature change of that much. All right. And then it is asking about the molar heat of solution in joules per mole. So this is a new term that we haven't heard before, so I wanted to spend some time clarifying that. Molar heat of solution. So like is implied by the units they gave you. Molar heat, if they're asking for that, they're asking for the heat per mole, right? The heat involved in that process per mole of reactant or thing you're dissolving. So this is actually like the enthalpy change of that thing. So delta H of the solution, that's another way you could see this asked for. Same thing. This is the heat of the solution, the enthalpy of the solution, the molar heat of the solution. Sometimes they would call it the heat of dissolution. Or they might call it the heat of dissolving. Those all mean the same thing. We're talking about what was the energy change from that process taking place, that physical chemical reaction of dissolving stuff. Okay, so this is a little bit tricky just like sign wise, at least for me. So I think I'm going to draw a picture. I think that's the best way to kind of get your brain around it, at least for me. So we are in a calorimeter, right? We're in a calorimeter. And we have added some salt. And you know, of course, in reality, when you add salt, like all the particles, they spread out and all the ions spread out. But we want to really think about what are we considering our system here? What are we considering the thing releasing energy? What are we considering the thing absorbing that energy? So I think it's kind of helpful to visualize it as if like all of the salt is in like one spot. And just kind of imagine that as like a nebulous blob of reaction. And that's just happening in one spot. And think about what's happening for that reaction. And then it's in the water. So what we're measuring here, we're measuring this interaction between the salt and the water. So like imagine like when you have your thermometer in this solution, right? What you're actually measuring the temperature of is the water. You're not measuring the temperature of like the ions on their own or anything like that. You're not measuring the like reaction on its own. The only thing we're able to measure is the water. So some people would contextualize that as like you're measuring the surroundings. So considering the water as our surroundings to tell us stuff about our system, which would be the reaction. So the reaction is releasing energy. The reaction is exothermic, which causes the water to heat up. So I think this will make more sense why I'm banging on this once we look at the math. The process is exothermic. So that's going to cause, like, look at what's happening here. The process is exothermic. We are releasing energy from the reaction happening. So that's what we're going to observe is the water's temperature rising because the water is absorbing the energy. The reaction is releasing energy. The water is absorbing that energy. And we're assuming that's happening all in our calorimeter. So we're going to see an increase of the water's temperature. Okay, so let's look back at this and see if we can figure out our heat of solution. So with that in mind, what we actually have measurements about is our solution, the whole thing, the surroundings here. So when I try to calculate, the first thing I'm going to have to think about, and I'm going to call that my surroundings just to like have a shorthand for it. The heat of my surroundings is going to be the mass of the solution, the C of the solution, and the delta T of the solution. So, and then there's a few like tricky things about this, like figuring out what you're plugging in for your mass. We are going to plug in the mass of the solution because that is the total mass of like the matter that is absorbing this heat. So you're going to be using 50.23 grams. See, sometimes they'll give you the heat of the solution, or I don't think you have to memorize the heat capacity of water. Maybe you do. It's probably a good idea to memorize it just in case. But a lot of the time when we have a solution, we're assuming it's the same as water. So maybe they'd give you water's heat capacity and you have to know that that's what you're going to use for, even if it's a solution, because it's mostly water, it's aqueous. So we're just going to call it. And then we're going to use our temperature change that we saw. So that comes out to being 346 joules. Now, the only tricky part about this, I feel, or one of the things that we have to really keep straight and really think about this process is understanding the sign of this. So again, we made measurements about the temperature change of the water, of the solution, but that is the opposite of what happened to our actual reaction. So the way that we could think about this is that the Q of dissolving is equal to negative Q of the solution, which is why Q of the dissolving is actually okay. Cool. So that is the heat involved. That is just like how much heat was transferred. But if we ever want to have an enthalpy, if we ever want to understand the molar heat, something like that, we got to consider like how much happened per mole. So all you got to do for that is put it over a mole, the moles that were involved. So negative 3460 joules over moles from up here. Joules per mole as question requested. There we go. Okay, so that's calorimetry. Again, we're going to keep practicing that on Monday. And we're also going to connect it to our next topic, which is phase changes. So physical processes in which we have a phase change. So let's consider this. So we've talked about this a lot, so maybe think to yourself, like, what is involved with the process of melting something, of boiling something, or of freezing something? Like, what is actually happening on the particle level? And we've talked about this a lot, so hopefully we feel comfortable with remembering that in a solid, like here's ice, there are very strong interactions holding together that solid. If it's a molecule, there's strong IMFs, or, a very structured IMF structure. If it's a lattice, then they're all held together very directly. Whatever it is, the force is holding together that solid. It's very structured. And then we have a liquid in which there are like kind of mobile IMFs, like as things come into interaction. And then there is a gas where they're totally apart from each other. If we're assuming it's an ideal gas, there's no IMFs at all. So the process of actually changing between these phases, if we are going this way, if we're going from solid, liquid, gas, we have to break IMFs or whatever it is holding them together. And breaking any kind of breaking any kind of chemical interaction like that, whether it's a bond or an IMF, will always require energy. And we can go the other way. Like, what if we froze water into ice, that kind of thing. Forming IMFs increases the stability and that kind of process always is going to release energy. Okay, so that's a key idea. When we make these phase changes, energy is required in that process. There is energy involved in that process alone. So a super helpful visual for this that we see a lot is something called a heating curve. So what we see in this heating curve, heating curve, it's showing the phase changes and effect of adding heat to a substance. Okay, so let's kind of orient ourselves here. We have heating time. So in this scenario, it's like, imagine you like put a pot on the stove, right? Like it's continually being added, like you're putting over a flame, you're continually adding heat to it. So what effect does heat do in each of those over time? What work is the heat doing? What is changing about your substance as you add heat to it? So the scenario here that it always like shows in this, it's always looks the same with like these plateaus and stuff. If you see 3 separate plateaus like this, let's orient ourselves. Down here in this part, we're assuming we're starting with a solid. So if you start with a low temp thing, you're starting with a solid. So in this little stretch of time, you have a solid substance. So let's observe what's happening. As you add heat to the solid, you can see the temperature of the substance increases in that range. So in that first range, we're increasing our temperature. So that's because when it's a solid and it's just a solid, all of that gained heat is going and creating more kinetic energy. The particles are moving around. So that's why we're observing a temperature change in that range. But at some point, as it heats up and as it heats up and as it heats up and its temperature is going up, at some point, the substance reaches its melting point. So this is the melting point of the substance. And I think it's worth mentioning, I think you should just know, water's melting point is 0 degrees Celsius. Water freezes at 0 degrees Celsius. So what we're seeing at this range, at the melting point, notice that it plateaus. We're not increasing the temperature of our sample, but we're still adding heat. So what is the heat doing if it's not increasing the temperature? What is happening at this point is melting. So at that temperature, we are still adding heat, but that heat is used to break IMFs. And this is called the enthalpy of fusion, the heat of fusion. Okay. So as you heat it up, it is not increasing temperature during phase changes because the heat is doing the work of breaking those IMFs instead of just becoming kinetic energy. Once everything is melted, then you'll notice that it starts increasing temperature again. So here, now we have a liquid. But it's just being heated and causing an increase in temperature. So still a liquid, the whole 3 section, it's a liquid, but it's getting hotter, it's getting hotter, it's getting hotter. And then we get another plateau. And let's get my writings in the way. But over here, this temperature is the boiling point of the substance. And for water, that is 100 degrees Celsius. So at this point, we're adding heat, we're adding heat, we're adding heat, but that heat is being used to vaporize, to evaporate our substance. All of that heat is going to be used for our enthalpy of vaporization, doing the work of completely breaking those IMFs so that our thing can become a gas. Once it's a gas, and all the particles are gases again, then we observe a temperature change. Again, so the gas can get hotter and hotter. So there can be water vapor that's over 100 degrees, but pure water at 1 atm at room temperature, or not room temperature, but at standard conditions, with nothing in it. Water itself, like liquid water, should not be over 100 degrees. It cannot exceed its boiling point because just by definition, it can only go to its boiling point and then it becomes its gas phase. And then the gas can become different. If we mess with the pressure or we add something to it, that's a little loosey-goosey, like it's not reality doesn't always reflect that, but in theory, the substance doesn't actually heat. So this would be the gas can be heated. So yeah, pretty cool. I think a super helpful visual. I come back to this a lot and I'll draw it when we do these types of problems. Like, as you're gonna see, or I'll clarify in a sec, but like it gets kind of crazy if you're trying to do calorimetry with these things, keeping track of all this. So come back to this visual. Think about what your heat is being used for at a certain point in the process. All right, to clarify these terms, I've just mentioned them, but delta H of vaporization, the enthalpy of fusion. I don't know why I put them in this order. I'm gonna do this one first because I don't know, I just feel like I should. This is the enthalpy change involved with melting a substance. So basically what we're talking about here is it's the energy required to break the interactions holding the solid together. Usually going to be IMFs for us. Versus vaporization, same concept, but we're talking about boiling. Right. So we got those guys. And it's worth pointing out here, both of them, as we can see in this process, both of those plateaus, we're adding heat for that. And that makes sense, right? Like we are breaking these interactions. It is an endothermic. So both of these by definition are endo. You can just add these labels if somewhere if you don't have space right here, but both are endo. So we're going to have positive values for these because it requires energy. So if you ever wanted to go the other direction, freezing something, solidifying it, or condensing something that's opposite of vaporization, it would just be the same number, but a negative value for it. So that's something to keep in mind. Again, the signs get really confusing with this unit, or like can be. It's easy to lose track of like your negatives. Always have that little logic check-in after you get a number. Does it make sense that my number is positive or negative respectively? Or did I perhaps drop a negative somewhere? Always something to check in with. Did I get a negative mass? Perhaps not. Perhaps we did something off. I also wanted to show this because I don't think I had before, just to kind of clarify the different processes. Mostly we're going to see fusion, melting, and vaporization. But there are these other phase changes, so we can go the opposite direction of melting. That's called freezing or solidifying. Condensing is when we take a gas from a liquid to a liquid. There are these ones also, again, pretty rare, but could be a thing. Sublimation, it's when it goes from a solid all the way to a gas, so no liquid in between. If you've ever seen dry ice, and like it steams off. That's what it's doing. Deposition, if you take a gas and squish it into a solid. Less common, but a thing. So any of these ones on the top getting more what's it called? Movement states. More entropy, but you don't know that term yet. The ones where we're breaking interactions are all going to be endo. These ones going the opposite way are all going to be exo. Okay, so the thing about this, like the big problem solving thing that is going to come up a lot is if you are doing a problem and a phase changes happens. We are using, if phase change happens, we are using heat to do the work of breaking those IMFs. Like, that is not the same thing as heat from raising a temperature. As we saw in the graph, there are some points in this process where temperature is changing, and there's some parts in this process where we are breaking those bonds. We have these rises and these plateaus. They are two separate processes, two separate things heat can do. They are two separate cues when you do these calculations. So if a phase change occurs, we're talking about this. We are talking about the energy required based on its enthalpy of formation or its enthalpy of, sorry, not its formation, sorry, that's later. Its enthalpy of fusion or its enthalpy of vaporization versus if I just have like water heating up, that is Q equals MCAT. Those are two separate things. So you really have to be careful thinking about, are we at my melting point right now? Or am I doing a phase change or am I just heating up my thing? What is the heat actually doing at this time? Which can be a little bit tricky as we're starting off. So let's look at an example. Gallium can be purified by melting. How much energy is required to melt 2 moles of the gallium, originally at 293 Kelvin? And we have all this information. Okay. So something to kind of orient yourself with this. Let's think about, I like this graph. I think it's very helpful. So I'm saying I have a sample that is at 293 Kelvin. And then I'm told that my melting point is 303 Kelvin. So I have a sample that's here and I want to melt it. So I need to raise it up to this temperature and then go through the process of melting it. So I have to heat it up to this temperature and then melt it all. Starting point, ending point. These are two separate heat processes. Two separate heat processes. So to calculate this, we're going to have to consider both of those Q's, get them and add them together. And I totally did not give you enough space in this spot. I'm so sorry, but try your best. So let's look at this. So my total heat required is equal to the heat of heating plus then the heat of melting. So I know when I heat something, when I have a temperature change, sorry, I know that's, sorry, that isn't great terminology for me to use because heat and temperature aren't the same thing. I meant when there's a temperature change by heating. I'll try to be clearer in the future, but we're just warming it up is what I'm trying to say colloquially. I'm sorry. But if we are heating it up, we know that we can eat. I did it again. Sorry, you know what I mean. If we're raising the temperature, we can use this equation. If we are melting it, we will use this equation using the heat of fusion. So that is a word you should be comfortable with, knowing that that is the same thing as melting. And now take a second, look at your data, be careful about your units. Keep track of the units in this problem. Perhaps you would notice that this is in moles. Just something to keep track of. Once you plugged it in, hopefully you would realize that that's in moles and this is in moles. So actually, this is going to be our molar. I'm just labeling it so we see. So we're actually can just plug in N instead of the mass, right? Because we want the moles to cancel out. We don't have any grams to cancel out. So I'm actually just going to use my number of moles. So I have 2 moles. I have a molar heat capacity of 25. Gosh, just gonna I have it written. I don't know why I keep wanting to zoom out. Okay. This. And you can totally do these 2 separately and then add them together later. I'm just gonna list it all out. And I had this temperature change, final minus initial. And then I also have the heat required for the melting. And then using my provided heat of fusion. So again, be careful about units. What you get out here is 520 joules. And my heat of fusion is in kilojoules per mole. So I have 11.2 kilojoules. The question asks for the energy in kilojoules. So I'm going to convert my joules into kilojoules, divided by 1,000, 0.52 kilojoules plus 11.2 kilojoules. The total heat required for this process is 11.7 kilojoules. Kind of a lot. But yeah. So yeah, this can get tricky. I think this will be like 2 Qs is probably the most you have to deal with for this class. But yeah, could be a lot to keep track of. So, be really clear about your process. If you want to write all your variables to one side, I think that's a good strategy. If you want to use subscripts to kind of keep track of everything, I think that's a good strategy. Write your units in your problem. It will be better in the long term, even though it takes a little bit more energy because it's so easy to accidentally drop something or you plug in the wrong thing. Okay. Why is delta H of vaporization so much higher than delta H of fusion? So we can confirm looking at our picture, we have a much bigger number for vaporization. So why would that be? So think for yourself for a sec. What does it mean to vaporize something versus melt it? Melting, we're going from a solid structure with very rigid IMFs to some IMFs, but in a more flowy state, versus vaporization, we're going from a liquid with IMFs to completely disparate gas molecules with no IMFs. So fusion should pretty much always, I think, yeah, this is going to be a very common thing. Fusion will take less energy because you are not breaking all IMFs. You're just breaking some, versus vaporization, you are breaking every single IMF, completely separating those guys. So something like that. I'll let you write that in your own words. Oh yeah, just before I move on, just again, with that little logic check, make sure it makes sense to you that this process would require energy. It's a positive number. We heated something up, we melted it. This should match that. Okay. We have a plastic. It often involves crystallizing the plastic in order to purify it. You don't really need to know what that means. All it means is that it's a super common thing to make something more pure is you heat it up and then you let it solidify again because some contaminants could come off. You get a better crystal of it. You get a better structure of it. It's whatever. But it tells you that while the plastic is solidifying, is the net flow of thermal energy. So flow of energy, we're talking about heat going into the surroundings or into the plastic, justify your answer. So we are solidifying, that's the process that's happening. So going from a liquid to a solid, think about what is involved in that process. When we go from a liquid to a solid, we are forming, and you know, if this is a real FRQ, write it out better, but whatever. Forming IMFs or whatever interactions. It's going to be IMFs most of the time. Sorry, forming IMFs, which means that that process will release energy, which means that the surroundings sorry, I forgot what I was writing. The question is whether it's going from the surroundings or into the surroundings or out of the surroundings. So something along those lines of saying that because you are forming those interactions, you're increasing the stability, you are releasing energy from that process, which means that the energy is going into the surroundings, not into the plastic. Okay. That's fun, I think. Yeah, cool. Okay. So how much heat in kilojoules is involved with solidifying 12 moles of PET from its melting point? So that's another helpful thing. We know it's already at its melting point, so we only have to worry about this one process, that just the melting. We're not talking about just warming it up. So for solidifying it, and we get our delta H of fusion. And that's super, like, it's so rare that they would like in textbooks and like in resources, they usually do like tables full of like fusions for like all substances. They're never bother giving you the other one because you just need to be able to recognize that melting is the opposite of the solidifying process. So the delta H of fusion is just equal to the negative value for our delta H of solidifying. Okay, so then when we go to figure out the Q for this, it would just be the moles of thing we have times its heat for solidifying. So that would be 12 moles times the negative 26.0 kilojoules per mole. So your heat involved in this process is negative 312 kilojoules. And the process asked for it in kilojoules, so we are done. Okay. So yeah, that's phase changes and heat involved with them. And that's it for this video. Have a good one.